guys, today I will show you how to solve ordinary differential equations by switching the variables. Say you have been given something like this: dy dx equals 1 plus 2y, and you need to solve it. So you need to find the general solution, which is basically happens to be a bunch of functions that works, that satisfies to your equation. And by the way, if you need extra help with introduction to differential equations and how to solve basic types, I do have a bunch of separate videos on this, and the links would be down below in the description box, and you would definitely go ahead and check it out later. Now, the idea is you want to switch top and bottom on the left side and on the right side of your equation. So you want to swap. So on the left side, you want to swap basically dy and dx, so you want to change their positions. And on the right side, so basically 1 plus 2y could be thought of 1 plus 2y over 1. So you would be left getting dx over dy. So again, I'm going to just swap them. And on the right side, you are left getting 1 over 1 plus 2y. Now, at this point, you want to separate the variables. So you want to split it up. You want to break it down somehow in order to get on the left side y terms and on the right side x terms, including basically dx. So, and by the way, I do have a couple of videos on separable, so sometimes it's called separable differential equations, and also the links would be down below in the description box, and if you are down to this, go ahead and check it out later. Now, in order to achieve this, so I'm going to multiply both sides of your equation by dy to bring dy to the right side. So again, I'm going to multiply by dy both sides of your equation. So always keep in mind what you do to one side of your equation, you have to do to other side. So you don't want to change the overall value of your equation. So what it does, basically, it clears off dy on the left side, what we wanted, and you are left getting just dx on the left side. And on the right side, let me just place dy on top. You would be left with dy over 1 plus dy. Now, we did separate the variables. So notice you have only dx on the left side and you have y term including dy on the right side. So, and at this point, we have to integrate. So we have to take indefinite integral or antiderivative, if you will, of both sides of your equation. So I'm going to integrate. So dx could be thought basically as a 1. So basically it's understood, it's implied to be 1, kind of a coefficient in front. An antiderivative of 1, recall it's just x. So you are left with x on the left side. Bring down the equality sign. And recall that basic integration, the table of basic integrals, if you will. So if you take the entire derivative of the right side, you are left with 1 over 2. Since you have this 2, the constant that attached your y term. Natural logarithm of 1 plus 2y. And I'm going to write this absolute value bars, or modulus, if you will. And don't forget to add the arbitrary constant of integration. Let's call it C1, and you will see the reason for this in a while. Notice I just added the arbitrary constant of integration to one side of your equation. So I didn't add this constant to the left side, because actually I did take the integral on the left side also, because it doesn't matter. So if you added two arbitrary constant of integrations to the left side and to the right side, eventually this constant can be moved around and they could be combined, they could add up just to one. So it could come up just to one arbitrary constant of integration. So it doesn't matter to what side you're going to add it, but you have to add it to just one side. So it's more than enough. Now, we are not done yet at this point, and our aim, our goal is to get your y alone if it's possible. So you always want to isolate your y term. So you always want to write y explicitly in terms of x, if they say. So if it's possible, again, it's my disclaimer, because sometimes it's not possible and you would be left getting something like implicit form of your general solution. It's also totally fine. But in this case, rearrange it, try to rearrange it somehow. Recall your basic algebra skills and try to manipulate and transform your equation in order to isolate to get your y alone. Now, recall the logarithm's properties. Since this C1 can be thought of as a natural logarithm of another constant, let's call it C2 or whatever you want, these two things could combine together. We could merge them, if you will, and you end up getting just one single logarithm on the right side of your equation. Let's kind of rename it as a natural logarithm of just C. That's why I told you I on purpose basically name it, I give it a name as C1. Go ahead, rewrite your left side as is, so you still have this x on the left side. Now, you still want to keep this constant a half in front of your natural logarithm. And again, when you have two logarithms, doesn't matter to what base, added together, so you could combine them as a one, and you could write it as a one logarithm with these arguments, with these insides being multiplied together. So this is property, it's a product property to be precise for logarithms. So you are left getting natural logarithm of C, let me put it front, times, and you have this argument inside 1 plus 2y. Now, so again, try to rearrange it. So I want to get rid of this kind of pesky coefficient in front by multiplying both sides of your equation by 2 in order to clear off this a half. So I'm going to multiply by 2 the left side and by the right side as well. So what it does, it clears off this 2. Now you are left getting 2x on the left side, and I'm going to go ahead and rewrite what's left over. Natural logarithm of C 1 plus 2y. Now, remember, always keep in mind, I'm aiming for y. So I want to get my y alone. I want to kind of pull it out, if you will. Now, recall that natural logarithm of something stands for the logarithm to the base e, and e is a special number, and math doesn't matter at this point. So it's implied, it's understood to be e, the base of the logarithm. And what I'm going to do, I'm going to just apply the definition of the logarithm, and I'm going to rewrite it using this definition. So I'm going to take this base, I'm going to pull it out, and I'm going to raise it to whatever I have on the left side, and it happens to be 2x, that's exponential power, if you will. So e raised to this 2x power, set it equal to whatever you have inside. So I'm going to pull out, I'm going to take out this inside part. So this inner part, c times 1 plus 2y. Now, things getting better. Y getting closer, closer, and closer. What I'm going to do at this point, I'm going to distribute this c, I'm going to open up, I'm going to remove these parentheses, and remember, when you have something outside, you take it and you multiply it by both terms inside. So you are left getting, just bring down, carry down this e to the 2x power, bring down equality sign, so it becomes c plus, and look, c times c gets multiplied by this constant too, so you end up getting, let's call it another constant, just let's call it for the sake of uniformity c1, all right, c1y, and you want to carry out this y as a term as well. Now we're almost there, So what I'm going to do, Since you have this c constant added to this term, I'm going to subtract this c from both sides of your equation. So you want to subtract c from both sides in order to get c1y, and I'm going to switch the order of terms. So you're left getting c1y equals, so e to the power 2x minus c. And finally, the last step. Whatever attached your y term, in this case it's c1, divide both sides of your equation. So, and we will get your y alone, isolated. So I'm going to divide both sides by c1. So this c1 goes away, it disappeared. And you are left getting y equals e to the power 2x minus c over c1. And that's going to be your general solution. It's going to be your general integral to this differential equation. Notice that you have two arbitrary constants, namely c and c1, engaged in your general solution. It might look a little bit awkward, little bit bizarre at this point, since we used to have only one, like it normally happens to be only one arbitrary constant of integration involving in your general solution. It's totally fine, it's totally valid. So sometimes you might end up getting something like this. So you have c and c1, two arbitrary constants in your general solution, in your general integral to your differential equation. Alright, I hope it has been helpful to you. Big thanks for watching and training your brain. I know everyone hates math, but if you like my video, please hit this like, share with your friends, leave the comments down below, and be sure to smash that subscribe button if you haven't, so you will not miss out my new videos.